We should probably start with a quick introduction of Philipp and me. Both of us are part of the community team. Yeah, that's a broadest introduction here. So today we basically have two sessions. I will talk a little bit about uptime. The first part of the session, we try to cut this down to like 25 minutes, have a few minutes for Q&A. This doesn't mean you should wait with the Q&A until the end. If you have questions, use the chat function, which is at the bottom of Zoom. And if you have a question, just make sure that you write to all panelists and attendees, which is something you can pick up at the two fields at the bottom. This way, everyone can see your questions. We will try to answer all questions either during my presentation, if Philipp wants to answer them, or we will just wait until the Q&A and collect those questions. So we hopefully will get to all of these questions. And the same, of course, applies for the second session as well. All right, let me share my screen. So hopefully you should see a presentation, and hopefully you should see a full presentation over here. And this will be the uptime introduction part. Just before we get going, a couple of housekeeping and logistics. I'm running on a bigger than usual display, an external one, so you may not see the full window right now. The way you fix this issue is basically to move your mouse button to the top, select View Options, and make sure that the window fits to your current window and resolution. This way you should be able to see the whole window. And of course, everything here will be recorded as well, and we will make this available over the next couple of days so you can revisit if you want. So what's the plan for the next 20 to 25 minutes? We will do a super brief introduction about the Elastic Stack, but that one will already be a little bit more about uptime. We will talk about what uptime is, into which kind of solutions uptime belongs. Then we take a look at Heartbeat, which is one of the components, and do a quick deep dive of what it's doing and how it's doing it. Then we will take a look at uptime in the Kibana UI, and of course, what the next steps are. What will be the next steps for you? What are the next steps in development? So you may have seen this image already a couple of times, and I think it shows really, really well where uptime actually fits within the Elastic Stack. Again, the Elastic Stack is just a set of building blocks if you want, and you can mix and match the different parts that you actually need. You may just need Elasticsearch for certain use cases. You mostly would like to have Kibana for management and monitoring. And in case of uptime, we basically use Elasticsearch and Beats to get the data into Elasticsearch, Elasticsearch to store the data, and lastly, Kibana. And Kibana is basically not only the UI or a dashboarding tool in this case, but there's a dedicated uptime UI within Kibana. So all of those three have basically a dedicated uptime use case here. And of course, you can again mix and match things like using machine learning with this kind of data. But for now, we stick for the most easy and simple use case. This is kind of a very simple data flow diagram, as the data for uptime stems from Heartbeat. The beat is on the left side, sending data over to Elasticsearch, and Kibana querying this. Optionally, you can use Logstash, but for the sake of simplicity, we will also not do this. All right, before we get to observability, I would like to do one thing, and that is getting up a cluster in cloud. And that one is the cluster that we will use in the next couple of minutes to get the Heartbeat data in. So if you log into cloud, let me make this a little bit bigger. You will have this login screen after logging in. You will get an overview about your running Elasticsearch services. I only have one, which I basically use to track my own location data. And you can always create a deployment. So in this example, we probably would like to have a virtual meetup for uptime. So this deployment is just a grouping of the different services I would like to run on AWS. I live in Munich, so basically Frankfurt would be the next data center to me. Then we have the version that we can select, but we'll just go with the most recent. You could select your deployment options here to go for a more concrete use case, but for now, iOptimized is the one that we can pick. And then you could either customize it or just create the deployment. Creating the deployment will take a couple of minutes. That's the reason why I would like to run this in the background while we keep talking about uptime itself. So where does uptime fit into the Elastic Stack? And Uptime is basically part of the observability toolset. And you may have known this already from things like gathering log files or metrics or APM statistics from your own application or the infrastructure UI. So there are a couple of pieces within observability and within the Elastic Stack. This is the logs UI, which allows you to search all across your log files. It supports things like highlighting, complete filtering, date ranges, and it's basically a very, very glorified tail minus F for all the data that you indexed into the Elastic Stack. Next up is the infrastructure UI. The infrastructure UI takes a slightly different approach by giving you an overview over your services that are up and running. In this example, there's a Kubernetes overview where the small squares are pods running somewhere across your cluster. The different colorization usually means different load or memory, depending on what you have selected. And for each of those pods, you can also go through other parts of the application and see in there what is actually happening. So you could go back to the logs UI and filter based on the pod. You could take a closer look at metrics or at APM traces or even in Uptime. So all of this data that comes from different data sources like log files, metrics, APM data or Uptime data is linked somehow within the Elastic Stack and can also be always viewed just from different perspectives to get an overview, not only of a single system, but of your complete system landscape. This is also part of the infrastructure UI. This allows you to see time series metrics. The metrics are usually kind of pre-selected, but you can always select your own ones. You can create graphs out of this or parts or visualization that you can then just reuse in your own dashboards if you want. And in this example, you basically see that there's a certain load of different CPUs and there's some peaks on the right side, but nothing I would be really worried about. The last part of the observability story here is the APM tooling. APM is Application Performance Management. Basically the ability to get more insight into your own or your self-written code, like measuring how long your checkout code really took, like not only the execution time on the back end, but probably also the whole execution time up to the front-end tooling so that you can tell, this is when I clicked the button on the client side, this basically went all the way down to my core code on my JVM running on the server side, and then back to the client, right? Because you not only want to know the runtime within like your own code, you also need to know how much was the complete runtime to receive user perception. And this also brings us to the next point, like what uptime is and how it fits into all of this. So you have metrics, you have log data, you have APM data. All of this shows internal application state, which basically means you see state from the inside. Like, this is how fast my SQL query ran. This is the amount of logs that were generated, exceptions that were thrown. But what you don't know is external application state. Like, what was the user perception of my service? How fast was it? Did I meet my SLAs? Those are all things that you cannot really tell by just watching at these numbers. And this is where uptime comes into play, which basically pulls your services from outside of your own data center, from the same positions or locations, if you want, where your client applications actually are. And this is a way that you can see, can I reach this host from where my clients are? What's my service response? What's my average response times? How long do TCP connections take? Or load balancing or handshaking? All these different kind of things that are also part of the overall experience, but are easily overlooked because you're so busy with the internal application state. Yeah, this is an overview. We're going to take a look at the UI in a second anyway. So I will just jump over these and explain this with live data in the UI. And the one thing I would like to talk about is how does the data get collected? And this is basically a special beat. It's called Heartbeat. It's one of those lightweight data shippers. And the way it works is that you can configure so-called monitors. Those are endpoints. So it can be an HTTP endpoint with a certain URL. It can also just be a TCP or an ICMP endpoint. And those endpoints are polled periodically, and the results are indexed into Elasticsearch. So it sounds really simple, but of course there are details to it which you always have to keep in mind. First off, like every other beat, you have the ability to basically spool results in case of availability issues or connectivity issues. But also things like if an IP address resolves to several, or if a DNS name resolves to several IP addresses, you want to make sure you check each of those services and each of those IP addresses. And this is what a Heartbeat is doing automatically. Next up is the configuration. It's basically YAML based, so you can easily check it into a version control system if you want. Also, you can just have a dedicated file for each of the monitors. So this is pretty easy to just keep and check in version control systems. And the key store is supported as with every other beat as well. So there's no need to store secrets in those files that you check into VCS. Okay, if you want to run this, you need an Elasticsearch instance. You also need a Kibana instance to watch the Uptime UI. You have a couple of options, hosting everything yourself with different packages, RPMs, Debian packages, Docker images, Elastic Cloud for Kubernetes, and the example we're going to use today is Elastic Cloud. If you would like to run this all within your own data center, then ECE, having a management interface on top of your installations, might make sense for you. Heartbeat is a little bit different because this one actually should run where your customers are. So it's not about your own data center. Of course, you can put a single instance in your own data center as well, but you should always keep in mind to also put it somewhere else, like across different data centers, across continents, depending where your users are. So this is not part of a standard installation package if you want, because it's basically running on the edge, which applies to most of your beats. The file beat is also running where the data is generated. Yeah, that was the theoretical part, and we will just switch over to the demo now. The first thing I want to show is a quick introduction into beats. I hope that this is big enough. So I have downloaded the Heartbeat file already. We can quickly unpack it. And I will copy a pre-prepared Heartbeat configuration file in there, which we're now going to take a look. Let me do this a little bit bigger. So there are a couple of things which are worth looking at. The biggest one are the Heartbeat monitors, those who are over here. And each of those monitors is basically a single check if you want, right? This first one is of type HTTP and polls this URL, sending a simple GET request. This check is considered successful if it returns an HTTP 200 response code. You could also add a custom name, which is always a good idea, and you should always do that if you can. You could add custom tags. With these tags, you could group certain searches together so that you know that certain checks belong together, and you would not be bound to come up with some interesting or weird naming scheme in order to achieve that. Then I have a check which will always fail, because this one returns an HTTP 404, which is by default considered a failure, unless you explicitly specify in the check that you expect a 404 to be returned. You can also send a custom body. This might make sense if you need to send a certain JSON payload, for example, and you want to be sure that this JSON payload is taken into account by your service. You can also make sure that a certain body is actually returned. So in this example, you can send hello world and we expect hello world back. If that's not the case, this monitor will fail as well. You also can use usernames and passwords. Again, those will probably be better stored in the key store to make sure it's a secret. And the last thing is that you can also check for certain HTTP headers. The other checks are of different types. As I said at the beginning, there's an ICMP check, which pings this host every 30 seconds. And there's another TCP check, which just makes sure that the Google DNS TCP server is reachable. All right, so this is the number of checks. The next thing to configure is where do we write this data to? And for now, we chose the console because I just want to quickly show what kind of data we are actually indexing into Elasticsearch. And this was already a full run to check the endpoints. And if we scroll up there, so this is the document that also gets indexed into Elasticsearch at the end. You can see there's some geo information, which is also put into the config file. So you can basically specify where the heartbeat is running. This one is running at my home office right now. The location is somewhere in Munich Central. There's a summary, so you can always figure out which monitors are up and down. This one is considered up, so the check was successful. If it connects to a TLS service, it also stores certificate information, so you can easily see when a certificate is expiring. We see that in the UI as well in a second. And there's some information about the round trip data. So you can see what part of the request took a little bit longer in context of HTTP. You can check the whole duration, how long did my whole request take. So this is all information that basically gets stored into Elasticsearch as well. So now our next step is to index this data into our freshly installed cloud instance. That one should have been deployed by now. We need to copy the password and put this into the configuration. So the next step would be to disable the console output and enable the cloud output. There are two things that need to be done. First is the cloud auth password. Second would be the ID. That one can be seen when you take a look at this deployment. You can just copy the cloud ID out there, paste it in here. And this is basically all the data we need. So what we can do now is we can launch a Kibana instance, log in as the Elastic user. This always takes some time for the first run. The reason for this is that there's a fair share of resources that need to be loaded and cached by the browser. So this only takes a little bit on the first login. And now we can take a look. We want to explore data on our own. Let me make this a little bit bigger for you. And on the left, there's a couple of applications. And the interesting one for us is the Uptime application nowadays. And you see that there is no Uptime index found because we have not started Heartbeat yet. Let's do that. You can run Heartbeat with the -e parameter to just see some more data. You can see here that the configuration apparently looks correct because we are connecting to a cloud instance of Elasticsearch, hopefully the one that I just started. There's a couple of setup steps taken, like loading an index template, setting up a write alias. And now the next step is basically checking when the data will get indexed. Let's see if we're there already. So, yeah, so we already had our first set of data being indexed, which pretty much happens after you start the Heartbeat. And now we can take a look to the different checks. You might remember that we configured a name for each of those checks. So that one is basically listed here. You also see that we had one check that doesn't have a name. You should always use a name because when I'm restarting the Heartbeat, this ID of the check can actually change, so you won't find it anymore. Just make sure you always set it properly. And as you can see here, there's an overview. You can see that there are 9 monitors up, so they were checked successfully. 2 of them are down. Let's take a look at the monitors that are down. And there's this one that is always failing. That one is always returning 4.4 HTTP error code, and we just do not expect a 4.4 being returned, so we consider the service down. The second one is the ICMP check, and the reason for this is that you need additional privileges under OS X to actually send ICMP packets, and the service that or the Heartbeat that I'm running doesn't have these privileges. So let's take a look at a check that is running successfully, maybe the easiest one. Check with a tag, for example. And you can see here where the check has been run from. So if you would have more than one Heartbeat, which is running the same check with the same name, you would see here the different location that we are actually trying to request the data from. You see also some information here that the SSL certificate looks pretty safe. It's only expiring in a year. There's also some information about the duration of this check. You can see here the first one took a little bit longer, half a second, and the other ones are slightly faster. They're still not super fast. I suppose that the machine running that is not super fast, and also that the TLS handshake negotiation just will take some time in order to get up and running. You can also see the last couple of runs here, the last 10. So you can see if there's any change just by checking it visually. And when we go back and check our Google TCP DNS check, for example, that one is just sending a TCP packet to see if the host port combination is actually reachable. And you can see here there's no hassle of some TLS negotiation or initialization. It just really connects to the port, and it connects to Google infrastructure, which is usually really, really fast. So instead of 500 milliseconds, this only takes 5 milliseconds. It's really, really quick. This one takes 8, but it's still super, super fast. So this is a nice way to just also see if something changed in your own infrastructure when you monitor these kind of services. So yeah, one thing is, as I said at the beginning, everything is kind of cross-linked if you want. So you not only have this separate Uptime application, it's really integrated with the rest of the observability package, which basically means you could now start checking this for host metrics or host logs if we indexed any more data with this. You could check for APM data in there, but we started with a completely empty cluster, so there's nothing that we can check for. But if you wanted, you could just really integrate this data really neatly together and start debugging issues starting from your application and potentially go all the layers up until you hit the user side of things. So let's get back to the slides and have a quick summary. So my quick summary here is that the internal state is extremely important to debug issues, but the external state knowledge is as important to just figure out if your service is really providing the guarantees that you think it provides, especially when it's about SLAs for things like APIs, but also just to make sure that your users can really reach your website. And understanding response times is important, and you should also monitor those things over time, and visualize changes over time is again something that is usually tremendously helpful, especially now when there's really different internet traffic patterns showing up on the daily basis compared to the last couple of months. And yeah, location. I monitored my application from Munich. But if your customers in the UK, or if your customers are in the East or West Coast, in Brazil, or Moscow or Japan, you may want to make sure that you have heartbeats in all of those data centers as well, and keep monitoring this one application. And maybe that also gives you an indication when you should probably split your application and run it in different data centers so that you are able to answer questions faster. Right? Just the time for a data packet flowing from Japan to Europe will take some time, given that you can travel faster than light. So once you get up and running, what will be the next steps? One of the interesting steps is auto-discovery. So you would be able to just add Docker containers, for example, based on certain criteria, and ping those instead of having to maintain the configuration manually. You may need to configure custom CAs. And you could also configure the scheduler limit and time zones. So the schedule limit, if you know how much polling the system you're running Heartbeat on can sustain, you could try and configure limits to make sure you're not getting over capacity. And there are also so-called processors which add more data to the document that are being indexed, like the locale or the time zone or the observer metadata. That was the location and the latitude and longitude of where I live, to make sure this could be properly displayed on the map. And of course, the security privileges are important. You may not want the Elastic user to basically have full access when you just want to add heartbeat data to a certain index. What's up next with Uptime? One very obvious thing is the Kibana alerting integration, which is currently being worked on. Same applies for the machine learning integration. Detecting anomalies, for example, for the duration, would be a very interesting thing to do, especially if you can figure out a maybe flaky data center or a flaky internet connection in there. Then the ability to support a cross-cluster search in the UI, so that you can take several heartbeat indices from different clusters into account when creating the UI data. And last but not least, something that is a generic topic within Beats is the central monitoring and management part, which will come in the future. All right, that's that. We're pretty much done with the presentation. I hope that I'm fairly in time. You may know the different services like Elastic Cloud. There's also an extended trial right now if you want to try that. And of course, if you have further questions outside of this webinar, there's always a discuss forum that you can ask. There's a dedicated Beats section. And within that, you can always ask all the heartbeat questions if you have, if it's about heartbeat. Otherwise, you probably would like to ask in the Uptime forum. And of course, regarding community of meetups, we are right now pretty much bound to the virtual meetups. We do have 3 different meetups there, one for Asia Pacific and Japan, one for North and South America, and one for Europe and Middle East and Africa. It's basically divided by time zone, but yeah, if you stay up for a long time, you'll probably want to check out the American ones as well. All right, that's it. Let's take a look at the questions. If I find the stop sharing button. Philipp, is there anything that I've missed?
No, there was one question coming only to us. It was if you can connect Tableau or get the data to Tableau. I shared the link with the right person. So there is an ODBC connector from Elasticsearch, so you can query the data in Tableau directly out of Elasticsearch, but that is a commercial feature, just as a side note.
Exactly, yeah, I don't have anything to add for that. Cool, if there are further questions, just put them in the chat. I'm happy to answer them while Philipp is basically doing the second session of this.
Ismail, I'm not sure which link you mean.
You should find if you click on chat and keep the chat window open, you should see a link which Philipp has written. Maybe that's what you're after.
Yeah, if you want to send it to everybody, there is, for me, it says all panelists or everyone, and then you can just switch it to everyone in meeting. Okay, if there are no further questions, and I'll let Alex handle that. Let me share my screen. Cool. I'll start with some slides and then we'll take this further into a demo. Though my machine is struggling a bit to keep up with Docker locally and Zoom, which are 2 of those applications you never want to run at the same time, I guess. So scaling your Elasticsearch cluster is probably a bit more of an advanced topic. So if you have a lot of data, that's where all of this should interest you. So once you have started collecting data, like Alex has shown you, this is where we're getting into now. Just like Alex, I'm also part of the community team. I mostly travel around normally. Right now, we're virtually traveling to everybody who wants to see us, but that's what we do. So to make your Elasticsearch cluster scale, what I want to cover today is Index and Snapshot Lifecycle Management, frozen indices, and we'll probably skip roll-ups for timing reasons because 25 minutes is not that long. But let's dive into that. So I have already started the demo because with Zoom running, it takes a bit longer to get everything up and running, and my data is being generated in the background already. So with lifecycle management, or actually index lifecycle management, what you have or want to have in general is a multi-tiered architecture. Generally, we would refer to that as hot, warm, cold, and then potentially delete. I once used the skull for the delete phase, and Alex complained that we should use the bin. So we're sticking to the bin for the delete phase now. So this is what we have there. The general idea is that you can use different hardware profiles on your machines, given that you have enough instances or enough data. If you only have 3 nodes in your Elasticsearch cluster in total, probably hot, warm, cold will not make all that much sense for you. But if you have more and you have a lot of data and maybe dozens of machines, then this is something that you want to be interested in. So hot is normally the phase where you're writing your data. Let's, for the sake of keeping it simple, assume we have a daily index pattern. And for today's index, you're writing all your data. And you probably also read most of today's data because you're interested in what errors happened in the last couple of hours and to just check those. That might be the hot phase. And then the warm phase could be yesterday to a couple of days ago. Data that is not actively being written to anymore, but that you still search more or less frequently, where you still research like, how did this behave before, or did we have this error before, or how many times did this error happen over the last week or whatever. So that would be like the warm phase. And then you have the cold phase. And cold phase is often more like, I don't know, I don't want to be too mean and call it the compliance layer, but it's oftentimes things you need to store and you will access them, but very infrequently. And you're also willing to wait longer. So especially on cold storage, you're willing to wait much longer for a query to return successfully because you don't do it that often. And you just want to keep the cost of the hardware down. So while on the hot layer, you probably have SSDs and you don't have that much data per node, the warm layer might already get spinning disks, but mid-size data size. And then the cold layer is you just put as much storage into the node as you can fit and just keep as much data there as possible because you know you will not search it that frequently and you're willing to wait a bit longer. And after some time, you delete your data. Whenever that time is, depends totally on your organization. Normally, when you ask the business unit, they will say something like 1 year. And then you say, okay, that will cost X. And then they will probably say, okay, 30 days are fine as well. Something like that we see every now and then. How that actually works in the code, and this is the one class where this is actually defined. This shows you what Index Lifecycle Management can actually do, both in terms of features and also how the actions are ordered. So all the phases have, except for the delete, have a set priority. That would be if a node starts up again, how quickly the indices should be accessible again. Like this is just the order of making the data accessible. Then you have an unfollow action in hot. Unfollow would be here for cross-cluster replication to actually stop following a remote cluster. Is a commercial feature, probably not that widely used. What is more common is the final step, the rollover, which is the one here. Why do we even have rollover? I said, let's keep it simple and do the daily index pattern before. The daily index pattern has one big downside. It might create very unevenly sized indices because let's assume you have a use case where we have a lot of logs today, but Saturday and Sunday are very quiet and then you have very few logs. And if you have the daily index pattern, you might just create, let's say 5 primary shards every single day. If you have very little data on the weekend, that will create very tiny shards, which have like a lot of overhead. So you don't want to do that. Rollover basically gives you 3 actions on which you want to create a new index. And those are generally based on time as well. You can also do by size or by count of documents. The default action that we would set normally is by size. So we would roll over after 50 gigabytes because for a login use case, that might be a nice shard size as well. Or after 30 days, because that's normally kind of like a sane value when you might want to roll over. So these two would be the default values that ILM would set when you use the beats for you. But you can, of course, change those. And then in the warm phase, you have a couple of the same settings. What you still have is read-only action. So this makes an index read-only to allow some internal optimizations. And then we have an allocation phase. The allocation phase can basically move the data from the hot node to the warm node then. That would be the allocation phase. By the way, just to connect the dots here, how would you make sure that the hot data is actually allocated to the hot node initially? Ideally in an index template. You could set it on the index directly as well, but that won't carry through. And if you have a rollover, won't be set for the next one. If you create the right index template, there you can assign that this data should go to the hot node. And then with the allocation action, you can then move it to the warm or the cold node over time. You can also shrink it. Shrink would be reduce the number of primary shards, which you might want to create higher at first to scale out the write operations. But later on, if it's read-only, you might want to reduce that because you don't need that parallelism. You can also force merge. This is when the data is read-only. It's a good idea to force merge to optimize the internal index structure, to force merge that down. And then in the cold phase, you have A lot of the same actions. There you have freeze. This is when we get to frozen indices, when we'll quickly cover those as well. So here you can freeze an index, and in the final phase, the delete phase, since 7.5, if I remember correctly, you can actually wait, or maybe it's no, this one I think is 7.6 actually. Wait for snapshot is you want to create the final snapshot to be sure that this data is part of a snapshot or backup in Elasticsearch. You want to wait for that action before you actually delete it. So this is what you could define. Let's look quickly at the code, how you would define that. So here, for example, this is my Index Lifecycle Management policy. These are demo values. Don't use these values in production. So here I said the maximum size of my index should be 5 megabytes or 5 minutes. Whichever is hit first will roll over the index to the next index. Then 5 minutes into being in the warm phase, we make the index read-only. We allocate it to a warm node here, and we set the number of replicas to 0. Also, we force merge it down to a single segment, which is definitely the right number for that tiny data set. And we shrink the number of shards. Maybe before going on, I should show you the index template, because that is what is defining some stuff here. So first, the index template defines that the number of primary shards by default is 2. So we're shrinking those 2 down to 1 in the warm phase. And here we're also setting that this data should be allocated to the hot node. So this index will always be created on the hot node, and then the ILM policy will then move it here to a warm node. In the cold phase, which happens 10 minutes later, we actually move it to a cold node and we freeze the index. So now it's a frozen index, and I will quickly cover that later on. And after 20 minutes, first we wait for a snapshot and we make sure we take the 10-minute snapshot, and then we actually delete the data. And this is what the ILM policy looks like. And this, what I've been talking, let me quickly reload that here. This has been running in the background. So here, this is the ILM policy at work. So we started with a metric beat dash and then all the zeros. That one is now already in the frozen state. So this is on a cold node. You can see this has also been shrunken down to a single shard and has 0 replicas. And you can see which policy kicks in first here. So this was a very small index. So here probably the 5 minutes kicked in before the 5 megabytes. And then we have the 1 or 00, whatever, 1 index, which was the next one. This has been shrunken down to a single primary. And it has, with the shrinking process, it is also being renamed from metric beat to shrink metric beat, whatever. And then we'll use an alias to actually make it still available under the old name here. You can still see metric beat 3 is still in the hot phase and will be shrunken down to warm soon to a single primary shard. And sorry, 2 is still in the process, and this one here is the one that is actively being written to. You can, by the way, debug this also quite nicely. If you head over to console, you can just pick the index you're interested in, add _ILM explain, and then it will show you a couple of things. Like first, it will show you how old is that index, because that is part of the age calculation of where you are in the life cycle, and then in which phase you are. So this one here is currently in the cold phase, and this just shows you which steps it has run through and when they happened and where you stand. And you could then do the same thing for the 1 index and see that this one here is now in the cold phase as well, but 2 is probably still in the warm phase. So here you can see this index is now in the warm phase, and this is just 6.8 minutes, whatever that is in actual time old. So here you can see how they're moving around, and this is what the ILM policy is doing for you. So this is not actually what I want. How the rollover happens is there's always this minimum age, which is either the index age since it was created or since it was rolled over, which is sometimes a bit confusing. And since in the recent versions, I think since 7.5, if you kind of backfill all the data, you could explicitly set that as an attribute on the index, which age this should have. So even if the data is just being created, but it's kind of like an older data set, you could still move it correctly through the index lifecycle pipeline. And even if you specify a lifecycle and it's kind of like happening with the min age before the previous step, one step cannot overtake the other one. So it's always hot, warm, cold, and cold cannot overtake warm, which hopefully makes sense. People sometimes ask like, okay, we've been using Elastic Curator for a while, and is that still around? Yes, it's still around. It has its use cases, but I think ILM is like the 80-20 solution. So we try to cover with 20% of the complexity and features, we try to cover the 80% of the use cases that you have. One of the main advantages of ILM is that it's running as part of the Elasticsearch cluster. So you don't have an external piece of software running, because Elastic Curator is just Python and you need to run that yourself, which is especially annoying if you want to offer a cloud service like we do, and then you tell people, well, you need to run this Python app on your own, on the side, on some virtual server somewhere. So ILM is much nicer in that regard because it's just part of the Elasticsearch cluster. But Curator is still more powerful. So if you have more complex backup policies, or if you have more than a single alias and you have like a maze of aliases for whatever reason, stuff like that you could do with Curator, but not with ILM. So there might be still use cases where you want to keep using that. Moving from Index Lifecycle Management to Snapshot Lifecycle Management, I've talked a lot about like how to move data around. So Snapshot Lifecycle Management obviously is there to take your backups. Let's switch to the code to actually show you how that looks like. So here we have a Snapshot Lifecycle Management policy. My policy is structured like a cron job. So this one here is supposed to run every 10 minutes. And then we actually name the snapshot the 10-minute snapshot. And then I give it a nice date pattern with it. I've created a custom repository that I just called my repository. We're including all the indices. And we also added a retention feature to the Snapshot Lifecycle Management. So I will only keep 30 minutes old snapshots, minimum 2, maximum 5, and then they will be removed as well. So you automatically clean up your snapshots. Since this is running locally, I've just mounted a disk, like my repository is a mounted disk that is shared between all the nodes, and that's where they take the snapshots. So let's quickly take a look at that. So while our data is moving in ILM around here, by the way, in ILM, you could also see that with the UI, but the UI is always kind of lying. So that's why I will stick to the API. If you just want to click around, you can do that in Index Lifecycle Management policies. You could click around the policy from Index Lifecycle Management. But let me head to the snapshots now. The snapshots are where you can see first, which repositories do you have? So here I have, like I said, this shared file system, the my repository that we have created. And then in the snapshots, you can see that right now I have created this one snapshot, the 10-minute snapshot at 14:29 that has been created with 11 indices, and it has 13 shards and nothing failed. You can also look at the policies. And in the policy, you can actually see that this is being created if it loads. But like I said, Zoom and Docker are making your life a bit slower. And you can see this is what we have created on the API, and this is just being managed in the background. And the same thing goes for the Index Lifecycle Management policies, which I didn't show you before, but let me quickly show what that one does. So my policy for ILM is called metric beat as well. The hot phase is enabled. It does maximum of 5 megabytes or minutes. By the way, in the UI, this was only added recently because before we did not support minutes. You could even say like we want to have a second or millisecond maximum age, but for production, those are definitely not advisable values. You don't want to have those because they will create tiny shards and you don't want to go there. And then you can see we have activated the warm phase, we're shrinking down, we have activated the cold phase where we're freezing, and then we have the delete phase, which will delete the data 20 minutes after the rollover. It doesn't support the Snapshot Lifecycle Management integration yet, but I'm sure that will come here as well. So these are the two lifecycle managements that we have, and they just keep moving data throughout our system. Let's see if the first index has already been deleted by now. And no, it's still in the frozen stage, but I'm sure it will kick, like, we must be coming up against the 20 minutes very soon. And then this one here will be deleted. By the way, one other thing that is kind of good to remember, especially for demos, by default, the lifecycle poll interval, how often the policies will run, I think are 10 minutes, if I'm not mistaken. For my demo, I have set that to 5 seconds so that you can actually see things moving around pretty quickly. But for a production setup, you probably have hours between index lifecycle management policy actions. So a 10-minute interval for the checks makes sense. For a demo, you want to have them quicker. That's why I set that to 5 seconds. Also, the retention schedule for snapshots, how quickly to clean up, I've just changed that to every minute so that stuff is being removed quicker. So these are just demo settings, but will make your life easier for that. One thing that is sometimes a bit tricky is that right now, you need to set the alias for metric beat and also specify that the first index that you create is the right index. So if you remember how aliases work, once you have multiple aliases or indices behind an alias, there would be read-only in the past. But now there is a concept called isWriteIndex. So even when you're writing to the alias that has multiple indices behind it, you could specify if a write operation is going there, it should go to that specific index. So your application never has to worry about, am I in metric beat 0 or 1 or 2 or 3? But you just write to the metric beat alias. And with that isWriteIndex, the write operation will basically go to the current hot index to be written. It's just something that you need to run in your setup process. But I'll share the repository afterwards, and then you can see how everything fits together and just try it out yourself. Okay, so heading to frozen indices. What are frozen indices? If you remember, there were closed indices. What were closed indices doing? Closed indices were basically something that was sitting on disk but was not accessible, and you would have to open them up to actually make them accessible. The advantage was they wouldn't need any memory. There were two other hidden gimmicks in closed indices, by the way, why they were kind of, you should have been careful to use them, though we have fixed those now. The first one was if you took a snapshot, a closed index would not be included. And the other one, if a node dies and needs to be re-replicated to another node, closed indices would not be included. Though we have in the 7 version of Elasticsearch 7 point something, we have fixed both of those. But before, you could lose data if you were not careful with closed indices. So that was a bit of a caveat, but it has been fixed. Now we have added frozen indices kind of like as a middle tier between an active index and a closed index. A frozen index is basically closed until you try to access it, then it will be dynamically opened up, searched, and then closed down again. So the idea is less memory usage, also slower reads, but you can just keep a lot more data on your nodes because they will not proactively allocate any memory. The trade-off here is that an index needs to be read-only, only then can you freeze it because you cannot write to an index. And how that actually works is it has its own thread pool. And by now, or currently, every node can only do one parallel search on a frozen index in parallel. And you can queue up to 100 requests per node then in that throttle thread pool to not overload a node. Maybe those are too conservative. You might want to increase them depending on your nodes and how you use them, but we opted for rather conservative operations. So when you search 200 shards, the first one would start searching on a node and would open up a shard and search. And then the next 100 would be queued and the remaining 99 would be rejected because your queue is already full. That's just how these work. So be careful when you open up very wide frozen index search operations because they might just be rejected because those settings are a bit conservative. Just to show you how this is working, and this is maybe a bit harder to show, but let's do this. So let me I'll create an index called frozen, and I'm adding David and Alex, and my cluster is more or less running. You can search those and you will find those two that I have just added. So David and Alex are there. Then we can do a force merge. The force merge is this recommended optimization to create the ideal Lucene index structure in the background before we actually freeze it. So now we have forced it down to one single Lucene segment. I freeze the index, which if you don't run Docker and Zoom in parallel, normally goes pretty quickly. Right now, it's a little slower. So now you can search the frozen index. What do you think will happen when I try to search this frozen index now after running the freeze operation? What happens here is maybe slightly confusing, because when I run that, it will suddenly tell you, well, I didn't find anything. It didn't say the index doesn't exist, but it just doesn't find any documents, which is a bit confusing. What you can do is you have to actually pass this parameter ignore throttled false. And this basically tells it, even if this is a frozen index, I know I really want to search this index. Basically, this is like for your protection, so that you don't run accidentally a very expensive search operation on an index where you think this is open and this will be cheap, but actually it's frozen and it's an expensive or slower operation. So this is why you need to pass this parameter to actually tell the index. You can then check the index and you can see, well, the index name is frozen, but otherwise you don't really see here that this is a frozen index. It looks like a regular open index, which is maybe a bit confusing. You can look at the thread pool. There you will see that you have run one throttled search operation here. So this was the search operation that I have been running before. To actually see that an index is frozen, you can, where's my operation? Somewhere you can, this is the one I want to see. Here in the settings, you can actually see that index search throttled true. This is the one setting that actually tells you that this is a frozen index. And don't be confused by the frozen name, because that is the name I provided, which adds some extra confusion here. What happens if I try to add another document? What if I want to join David and Alex? This will obviously be rejected, because that's a frozen index and this is read only. So what you would have to do then is you would need to unfreeze the index. Then I could add myself again, and then it's a regular index. So this is how the unfreeze works. So freeze and unfreeze are just like open and close operations. They take a short amount of while, and then you can just use the index like normal. But the frozen index is read only, and there's no easy way around that. One thing that you can add here is the pre-filter shard size, which is basically another round trip before doing the actual search operation, and it excludes shards that cannot match. So for example, if you have a date range filter and you search for something in the last 24 hours, and then in the metadata of the index, you can already see that this index only has data that is older than 3 days, your search operation will never try to find anything in that index, but will immediately skip that. And you can set that explicitly as how quickly you want to set that. For frozen indices, it probably makes sense to set that to 1, to always check if you have more than a single shard that you're searching, to actually check if it can even match. By default, it only kicks in, I think, if you search 128 shards or more. Only then would that pre-round trip be run, because otherwise it's maybe more overhead, but that always depends on how long a round trip takes for you and how expensive the search operation is, etc. For the sake of time, I guess we'll skip rollups. Or just to give you the idea of rollups, it won't work for logs. If you have metrics, you probably calculate or collect very fine-grained metrics today. But over time, you might want to roll them up into or pre-aggregate them into bigger chunks. So after a week, you might not be interested in 10-second intervals, but in 5-minute intervals anymore. And rollups basically aggregate that together for you. If you're interested in that, it's part of the repository, and I'll show you the link in a moment. So this is the link where you can get all the code. If you clone the repository, all you need to do is you run docker compose up. It will pull the right images. It will start that cluster, and it will then with ILM start moving data around. So it's using metric beat to actually collect metric data from the cluster itself, and then moves that through all the different lifecycle phases, takes snapshots, rolls up the data that you have collected, etc. So this will all drive itself. Just start it up, watch it for 5 minutes, or come back half an hour later, and you see how data is being moved around. So to recap, what we have seen is lifecycle management, both for indices to move different hardware profiles, or maybe just delete. So even if you have a very small cluster just with 3 nodes, maybe you don't need a warm and a cold phase, but you probably want to have a delete phase, because at some point you want to remove old data. Also, snapshot lifecycle management, to take a snapshot of your data, will probably come in handy. Frozen indices provided a new layer to use less heap and make your data still accessible if you pass in the right parameters. Also, by the way, in Kibana, you need to flip a flag that your Kibana dashboards should include frozen data. It's in the settings, you need to flip that as well. Otherwise, Kibana will also silently ignore any frozen indices. But again, this is for your protection, so you don't run any expensive accidental operations. And then rollups to pre-aggregate metrics. Obviously, this only works for metrics and not for logs or traces. So those can be then calculated. And if you want to get all of that set up for you, you can just get it on cloud, where you just say, like, this is my high IO and high storage, like this is the hot and this is the warm layer. These two you can just click together, and then with ILM you move your data around, and you have a more price efficient data structure, because this one here will have high IO and will be good at storing your data and doing quick searches. This one here will be more price efficient for the amount of data it can keep. You can see this one, for 4 gigs of RAM, we have 240 gigs of storage, whereas this one has 800. So this one will be able to keep around quite a bit of more data. So that will keep the cost down for that one. Under the QR code, you can get the slides, though I can also throw the link into the discussions to get the slides. Are there any questions? Let me stop sharing. Let me add the slide link. If you want to try that out again. So
yeah, we will also add the slide links to the community page, so people can just visit the event page and get the slide links as well.
Yeah. Any questions? Anything unclear? Especially ILM can be a bit complicated at first, also later on. I think our support is handling lots of ILM cases over time.
Yes, also the Discuss forum has an ILM use case, but don't hesitate to ask if anything isn't clear. It just means we have to improve the API, and that is perfectly fine.
The documentation has already improved quite a bit. So the documentation for ILM is actually pretty detailed and good. If you have any questions, it's a good place to start. Or Discuss or Slack, like all those places. Cool.
Yeah, I think that's that. We're also hitting the hour. So if there are no more questions, we should probably call it a day. Thanks a lot to everyone attending. There will be another session next week about APM. So if you're interested in that as part of the observability story, just make sure you come by there as well. That one has also been announced today on the community website, so you can already register just to make sure you don't forget with all the stress going on. And yeah, that's it. Thanks a lot for coming by. Thanks a lot for Philipp to also run this presentation, and hopefully see you next week.
Bye, everyone.
Bye there.